Our next speaker for today is Shen, who is a principal research scientist at Microsoft Research and is a data science manager of the Microsoft Academic Project, where she works on data mining and NLP for understanding large-scale corpora with associated network systems. Iris, can you share your screen now?
Hello, testing.
Yep, sounds good.
Okay, so I can start?
Go ahead.
Okay, yeah, thanks for Kyle's introduction. I'm really honored to share the latest efforts in our team that continuously enrich the lab-scale scientific taxonomy by incorporating both the language features as well as the graph features. So here is the outline of this talk. First, I would like to share some high-level background information about our bigger scope project, the Microsoft Academic Project, and then I'll specifically answer the what, why, and the how questions on the taxonomy enrichment in our project. The what part would be more focused on what has been done and delivered, the current status. The why part would be focusing on the current limitations we observed for our existing approaches. And the how part, we will talk more details on a two-stage approach for the taxonomy expansion. First is on the discovering the new concept. The second one is how to incorporate those newly discovered concepts into the existing taxonomy. And at last, some challenges and ongoing efforts discussion. So here is some background about the Microsoft Academic Project. So we are the Microsoft Academic team within Microsoft Research Redmond. And we started this project since year 2014. Our main deliverables are three parts. The first part is academic domain specific knowledge graph. We call it as a MAG, Microsoft Academic Graph. This is a graph contains the 6 types of academic entities. Basically, it describes, if you look at the star schema in the middle, it describes which author supported by which institution or affiliated with have made what claims at in which publications, at which venue, and when, what time. So in this graph, currently, we have about 500 million entities and around 3 billion relations. Among all these 3 billion relations, about half are citation relations, which means that we have a little bit over 1.5 billion citation pairs currently. This graph is quite fresh. It's updated weekly, and it can be also freely accessible in Microsoft Azure storage. The other 2 key components are the Microsoft Academic Knowledge Exploration Service. This is used to index the behind the knowledge graph content and enable a front-end search UX for a semantic search or exploration powered by backend data. So you can consider in current MAG project, one of the core capabilities is to leverage the computing power to understand and organize all the academic publications. To achieve this goal, currently we use a 3-step approach. The first one is we discover a comprehensive list of scientific concepts from some external data sources, such as Wikipedia or the Unified Medical Language System, the UMLS. The second stage is to recognize on each paper what domain, subdomain, and more specific or granular concepts are associated with the paper. The third stage is leveraging the second stage result, and we apply the DIH principle, which is a distributional inclusion hypothesis to construct a 6-level hierarchy. As of now, we have in total 740K concepts. About 75% of them are organized in a 6-level hierarchy. The top 2 levels are manually curated, which we cross-referencing a couple existing scientific classification schemes, and the remaining 500 plus K are all automatic generated based on the distributional inclusion hypothesis, or sometimes we call it the subsumption rules. So regarding the updating schemes, we keep on looking at the new ingestion or the contents coming from the Wikipedia and the UMLS, but because of it's kind of a major efforts to update the taxonomy, so we only update, apply the same DIH principle and update about every 3 or 6 months frequency. So what's the challenge with the existing approach, right? So we will see the very first one is we would like to discover the emerging concept faster from the latest scientific publications, because anyway, they are the original birthplace of many new concepts and methodologies from the very first place. So can we read the new papers to recognize and discover them? And the second challenge is we always have quite a lot, we call them as a low resource concept, which means that there are not many papers are talking about them, at least not in the title or abstract, which are the existing textual information or corpus we are using for the tagging and the taxonomy construction. If they are low resource, so the subsumption principle wouldn't be able to apply, and how can we do better on this type of concepts? And obviously, the last but not least, we are a deployed production system. We definitely need to address the engineering concerns on the scalability, as well as the usability requirement. We need to consider the taxonomy shouldn't be changed that much, cross-run. Okay. So how do we address these challenges? We use a 2-stage approach for the overall taxonomy and concept in the taxonomy to decide if it would be the best candidate to attach for any new coming concept. Hello, hello.
Yes.
Yeah, where did I been cut?
Yeah, we lost you for the past maybe 30 seconds. So if you could go back.
Okay, past 30 seconds. So I guess I could just quickly talking about the 2-stage approach, right? I talk about the self-supervision part because we leverage from our existing systems concept tagging result and the taxonomy construction result as a supervision signal to train the model. The reason that we rely on the self-supervision instead of collecting the external some manual labels for the training purpose are due to like 2 main limitations. The very first is the overall our concept space are so large in the scale of millions. And the second is our labeling effort, it's not just some regular or general knowledge label. It's usually requires the labeler have quite in-depth domain knowledge to generate quality results. And our corpus have contents across almost all the disciplines. And obviously, it's really challenging to recruit the scholars around the diverse fields to give us comprehensive coverage. So the majority or even the ongoing efforts we are exploring are mostly around the weekly supervision or the self-supervision. So now comes to the first stage, right? How to discover the new concepts. In this stage, for the scalability concern, again, we decompose the problem into two smaller subproblems. The very first subproblem is just to recognize the words or phrases in a sentence if it is talking about a scientific concept or not, without worrying about which concept it's talking about. So this one, with obvious the recent success of the transformer-based models, we use a BERT large pre-trained result and fine-tuning a NER-based model. But here we did a modification. Instead of usually common have 4 or 5 different entity types, we just reduce it to a single type. We call the academic concepts. And then it's essentially reduced to a binary classification problem. So how we collect or generate the self-supervision label? We first harvest, we call the high quality papers from our corpus. By high quality, we mean they have a good amount of citation and coming from the prestigious venues. And we will use the existing list of concepts in our system and to go over all those titles and abstract coming from those papers and select the 500K labeled sentence when they are talking about specific concept. For example, in this sentence, the network embedding is playing a critical role in network analysis. We can recognize the network analysis is an existing label, and we wish to train a model which can tell us the network embedding is a good candidate for a new concept. And you can see that we harvest the 500K sentences from the computer science and the 500K sentences from the medicine to test if the model trained actually domain sensitive, which the result is not surprising. We can see if a model trained from the CS corpus, it can do pretty good job for inference on CS corpus, but do relatively really poor on the medical corpus. So this align with our initial hypothesis or general intuition. So we would train the model based on a few high-level clusters of our top domains and apply them separately instead of a general model across covering everything. So the next stage, once we have this candidates of those phrases as a potential new concept, we would like to recognize which specific concept they are talking about. So in this stage, we leverage the Bing API, or I would say we kind of leverage all the web documents out there in the web. So there are 3 possibilities for a new phrase. It could be first, a synonym of existing concept, or second, several new phrases together are representing a new concept. And then we need to cluster them together and select the canonical form and obtain a description. I'll share why we really need a description. And the third possibility, it could be a noisy term and nothing about a scientific concept, and we just discard. So we send each newly discovered terms or phrase as a query to Bing API and collectively analyze the top results of all the queries. These would help us to cluster synonyms if they share the same URLs as their top returning results, and also returning snippet of the web page if they are coming from a prestigious website, for example, on the medical domain in WebMD, and then they can be a good candidate to use as a description. And for the domain, for the top search top results, domain trustworthiness, that are the signal we leverage to help us decide if this could be a legitimate concept or may not be. And regarding the canonical name selection, we will just use the frequency of a term's appearance in the corpus. The most frequent one win and will be selected as the official name of the concept. So from the right-hand side table, you can see we already have the Wikipedia and the UMRS like 660K. And over the past several months, we harvest about 80K new concepts with the above described model and already ingest or incorporated in our current system. Okay, so once we have those newly discovered terms, where should we put them to the taxonomy, right? So in this work, I'll introduce a work leverage the position enhanced GNN with a self-supervision signal to expand. So this is a work done by a summer intern with us last year, and this work has already been published at the web conference earlier this year. So let's first define the problem. What's the input? The input is the existing taxonomy and a set of new concepts, and the output is intent to include all these new concepts to expand the taxonomy. And here we have some specific assumptions. Very first is we need each new concept or even all the concepts in the existing taxonomy with some initial feature vector. They are currently used as a language embedding coming from their names and the synonyms as well as the definitions. So you see why we really require for the new content that we are adding in, they should have a few sentences of definition to help us generate a better quality initial feature vector. And also we assume we don't modify the existing taxonomy and we only focusing on finding a parent node for each individual new coming concept, which means that all the new coming concept can only be added as a leaf node for the taxonomy. Here, I would like to introduce a few terms first to describe the general idea, right? So for the new concept to be added, we call it as a query term. For every node in the taxonomy, we call it as an anchor term. And our approach trying to learn a good matching model so that it returns a score between a query and anchor pair, that the number or the score tells us how likely the anchor concept is a parent of the query concept. So the key idea here to leverage the GNN is we do not only want to leverage the anchor concept itself information, but also incorporate the one-hop neighbors information. And then we represent its ego network, which is a one-hop neighbor network, to represent the anchor concept. And also we would add the position information, which are relative to the query concept to the ego net, which can best or better help us to decide which place are the best candidate. And we call our new model as a Taxo expand, the abbreviation of taxonomy expansion. And there's three key modules we have in this in this work. The first one is the graph propagation module, which aims to learn a good node representation. And the other is a graph readout module, or you can consider as a graph aggregation module, which is learn a good ego net representation. And the last one is a matching module, how to best match between the query and the anchor. And so you can see here from the color code, the relative position to the query node. For example, the parent, the ego node as a parent, the the purple as a grandparent and the sibling node, these are really helpful to improve the performance. I won't cover the detail of this, and you can help to read the paper to see the improvement that they have.
Iris, maybe a couple minutes.
Okay, sure. Yeah, so here is again, we also use a self-supervision to coming from the existing taxonomy to learn the matching model parameter, and we group all the pairs that share the same query concept, which have exactly one positive pair and the rest are negative. And we all optimize over a new info NCE loss, we call that, aim to have more robust to the label noise. Okay, I won't cover too much details about this, but we do test on the Microsoft Academic CS corpus and the full corpus. And we'll say it's really improved a lot over other traditional models previously used for this type of expansion. However, I would like to say that even on the domain-specific model, the hit at 1 or 3 are almost 20 or 40%, but still it's very hard to directly apply to the production system. So we're still tuning and to see how can we best leverage this work to our current production. So really quick, the continual challenge always the quality of the existing concept. We still have lots of synonyms. They are considered as separate concepts. How can we better merge them together? And we always have trouble around those low resource concepts. And the ongoing efforts is we really wish to combine the language and the graph features together to learn simultaneously to see if it can have a better result. At the same time, if we can join optimize both stamping and the taxonomy construction to generate a better result or overcome some current limitations. And remaining are mostly the engineering efforts. We really wish to have more text information for our training and also some other external high quality terms or result, how we can best leverage those into our system. Yeah, so it's really quick summary is we talk about the taxonomy enrichment with two-step concept discovery and taxonomy extension, leverage the textual and the structural information, aim to reach the freshness, scalability, and take care of the scarce resource. And yeah, we currently use a transformer-based model on both language and the graph separately, and leverage a lot on self-supervision. And our data are freely available. I have all the resources on the very last slide, and I believe we will also share the slides. And if you think it's interesting or relevant to your research, feel free to download a copy and play around.
Awesome, thank you, Iris.
Thank you.
I think we have time for one really quick question. David asks, how does MAG discard, if it does, articles of dubious standing, say pseudoscience or extremely controversial content, from its publication index?
Sorry, you mean how to discard those low quality content? Is that the question?
Yes, I believe so.
Okay, yeah, so for that, we actually leverage some external or the whole web information by calling the Bing API to see if the top results are really coming from the more prestigious or reputationable domains. And then we will do the classification mostly from there.
Awesome, thank you, Iris.